Welcome back to the module on one-sample hypothesis tests. I'm Dr. Ellen Gordon. In this video, we'll cover another example of a one-sample t-test. If you refer to your prep assignment, we can read the research description. One of Best Teas Bottler's most popular products is the 16-ounce or 473 milliliter bottle of sweetened green iced tea. Annual production at any of the given facilities is in the millions of bottles. Data on past production show that the distribution of the contents had the desired average fill, which was a population mean of 473 milliliters. 20 bottles were randomly selected from the production line, and the data is presented in this worksheet. Conduct the appropriate hypothesis test with a significance level of 0.01 to determine if the mean fill of all bottles produced by the current process differs from the desired level. The first step is to identify the appropriate statistical test. In order to do so, we can complete the descriptive statistics table. So we are comparing two means. We're comparing the current mean fill of the bottle to the desired or advertised fill. For the current mean fill, we have 20 bottles, so that is a sample, and we can use Excel functions to compute those statistics. We can use the average function to compute the mean. For the standard deviation, we do .s because we're working with sample data. And we can use the count function to determine the sample size. The desired or advertised mean was provided in the research description. It's 473. That is a population mean. And you can see that it wasn't accompanied by a standard deviation, so a standard deviation was not provided. So whenever we do not know the standard deviation, we can just type in a question mark. And again, it was a population, so there is no sample size, so we can put NA. So we are comparing two means. For one group, we have sample data, and we're comparing it to a population mean, and we do not know the population standard deviation, so that would be a one-sample t-test. The next step is to identify the case. This handout is posted on ISMS. I recommend when you complete future problems to use it as a guide. If you remember, the case is based on the alternative hypothesis, and it can be two-tailed, one-tailed left, or one-tailed right. You can see here in the research description, it says to conduct the appropriate hypothesis test to determine if the mean fill of the bottles produced by the current process differs from the desired level. So we're looking to see if there's a difference. There's nothing in this research description where we predict that they're overfilling the bottles or underfilling the bottles. We just want to see if the current fill is different. So that would be a two-tailed test. The next step is to identify the hypotheses. Again, the null hypothesis is the hypothesis of no significant difference, and the alternative hypothesis is our research hypothesis. Our research hypothesis is we think or are looking to see if there's a difference between the current fill and the advertised fill. Here's the hypotheses in symbols. We're conducting a two-tailed test, so this is our set of hypotheses. Again, H1 is the alternative hypothesis, and we're looking to see if there's a difference. So the two means would not be equal. And then the null is the opposite of that. So the null is that the two means are equal. The next step is to identify alpha. Alpha is presented in the research description. You can see right here it says a significance level of 0.01. Significance level is another word for alpha. So our alpha is 0.01 or 1%. Alpha is an objective rule on when to reject or fail to reject the null hypothesis. We're conducting a two-tailed test, so we put alpha into both tails. If our test statistic or our sample mean falls in this yellow shaded area, it will fall in the rejection region and will reject the null hypothesis and accept the alternative. If our test statistic or our sample mean falls in the middle, we'll fail to reject the null hypothesis. The next step is to compute the critical values. We're conducting a two-tailed test, so these are the Excel functions we'll use. Remember, for a two-tailed test, you have two critical values, a lower and an upper. They'll be the same number, it's just the lower will be negative and the upper will be positive. The formula for the lower critical value is -1 times t.inv.2t, and then it asks for the probability, which is alpha, and then the degrees of freedom, which is our sample size, -1. For the upper critical value, it's t.inv.2t, and then we indicate the probability, which is alpha, and the degrees of freedom, sample size minus 1. Again, the critical values are the t-scores that are associated with alpha. We had an alpha of 1%, and we split that into the two tails, so we have 0.5. So a t-score of 2.86 cuts off the top 0.5%, and a t-score of negative 2.86 cuts off the bottom 0.5%. The next step is to compute the test statistic. First, you need to compute the descriptive statistics, which we already have done. Now we can compute the t-statistic. This is the t-score for our sample mean. The formula is the sample mean minus the population mean divided by the sample standard deviation divided by the square root of the sample size. This is the same or very similar to the test statistic for the one sample Z. The only difference is we're using the sample standard deviation instead of the population standard deviation because we don't know the population standard deviation. The star denotes where our sample mean or our test statistic falls on the standard normal distribution. The next step is to compute the p-value. This determines the probability or the percentage associated with our test statistic. We're conducting a two-tailed test, so we'll use this function. The function is t.dist.2t, and then what we're going to do is for x, we're going to take the absolute value of our test statistic, so we use the ABS function, and then we have degrees of freedom, which is our sample size minus 1. Again, p-value should be formatted as percentages to 2 decimal places. Here's a visual depiction of our p-value. It is the percentage to the right of our test statistic. Next, we can make the decision regarding the null hypothesis if we're going to reject or fail to reject. For the p-value approach, we compare p-value to alpha. If our p-value is less than alpha, we reject. If it's greater than alpha, we fail to reject. Our p-value was 0.5% and our alpha is 1%. Our p-value is less than alpha, so we will reject the null hypothesis. We can also use the critical value approach to determine if we're going to reject or fail to reject. For that approach, we compare our test statistic, our t-statistic, to the critical value. Our critical value was 2.86, and our test statistic was 3.17. You can see that our test statistic falls farther out on the tail in comparison to the critical value, so it falls in the rejection region. That means we'll reject the null hypothesis. So we'll indicate that we are going to reject the null hypothesis. The last step is the conclusion. Whenever you reject the null hypothesis, your conclusion is the alternative hypothesis. So we're going to conclude that there is a significant difference between the current fill and the desired or advertised fill of 473 milliliters. We'll then want to include in our conclusion what we think is going on if the data looks like the bottles are being overfilled or underfilled. And to determine that, we can look at our descriptive statistics. So here is our sample mean. It's 474, and that's greater than 473. So that suggests that the population mean for the current fill is greater than the advertised or desired fill. So now we can write our conclusion. There is a significant difference between the current fill and the desired fill of 473. The data suggests that the bottles are being overfilled. That is, the current mean is greater than 473. So in conclusion, we tested the null hypothesis that the current mean fill has a population mean of 473, which is the same as the advertised fill. We observed a sample mean that fell all the way out on the tail. There was less than a 1% chance that we would observe that sample mean if the population mean was really 473. Thus, we are rejecting the idea that the population mean is 473, and we're concluding that it's greater than 473.